Okay, we're going to move into cast-in-place concrete buildings, which is a very common building to be retrofitted because their older buildings are typically not ductile and weak and have many other deficiencies. We have 3 chapters, as I mentioned, when you're talking about model building types. We split up the shear walls into several different, or 2 different kinds, but we have the standard FEMA model building type concrete moment frames, which is really not the correct term. It should be just gravity frames, because often these buildings are just beams and columns without actual design for lateral forces. Then we have the C2F, which is the concrete shear wall building that has a gravity frame system, but either has a archaic shear wall design or just has some incidental walls around stairwells and so on. And then we have the C2B, the concrete shear wall building, which is a bearing wall, typically a hotel or a motel that has bearing walls between every room, and often has precast floor plates with a topping over the top. So these are our 3 cast-in-place concrete chapters. We discuss the differences, and of course these buildings sort of meld together when you end up with a C2F gravity frame shear wall. As the shear walls get fewer and fewer, you end up into a C1, and so there's discussions about how these building types interact. So the moment frame is often not designed as a lateral frame, but only for gravity. It could be a column beam system. It could be a column and slab system. The gravity frame often has essentially complete gravity frames that could have moment resistance just like the C1, but it has some walls, and that's why it's a different model building type. And the bearing wall almost never has any columns, maybe a column at the first floor where they have put in some sort of a meeting room. The moment frame might have some incidental concrete or masonry walls in various states of connectivity. At some point, again, it merges with the gravity frame shear wall, because both of those buildings may just have incidental walls. So it depends upon really what is the predominant lateral force system that you want to deal with. The C2B may have these precast floor panels, and the early versions of these buildings, they put the precast spancrete or whatever it was on either often reinforced masonry, but also precast or cast-in-place concrete, and they may have only 1.5 inches or so of bearing, so it's a very scary system. The ties, the cover of concrete may not have very good ties across those walls, so the panels may very well split and fall off. So that's the connections of that building is scary. And the concrete frame, if it's considered a frame, if you actually analyze the frame and it's not passing the standard ASCE 31 or whatever, it's probably because it's too weak or it's non-ductile. I mean, those are going to be the classic deficiencies. If the shear wall building does not pass the standards, it probably is also too weak, or the walls may be shear critical, and will be shown that they will degrade very quickly, or if it's a taller building, the shear walls will probably be too flexible, and you'll end up with too much drift for the gravity frame to handle. If the bearing wall doesn't pass your evaluation standards, it's probably that they're shear critical, or you might have a weak story at the base because some of the walls stop for the lower room. So these are the typical deficiencies you might find in these buildings, and of course you have the configuration deficiencies that might trump everything if you have a weak story or soft story or plan shapes that are unusual. These 3 chapters have similar rehabilitation techniques, and the reddish color is the chapter in which the different rehabilitation techniques is placed, but the gray indicates it's also applicable there. So we have the added steel frame for concrete in the C1 chapter, but you could also add a steel frame in these other steel brace frame in these other two buildings, and so on. So these are the techniques that we have in the C1 building, and then these particular techniques are really more related to walls, so they're really related to C2B and C2F. So we've placed all of the techniques just location-wise into the chapter with C2B, but they're also applicable to C2F. And of course this is all written in there, but as I said, you don't want to repeat the techniques and put it in every chapter where it might be used. So the moment frame rehabilitation techniques, again, we're not going to go through every one of these boxes, but you've seen it over and over, so it's a guide to get you to quickly to the right technique. And the particular moment frame version has quite a few, and the C2F has quite a few. Those are the ones in the dots that I previously showed you. And the C2B has quite a few techniques, but they're really referencing to other chapters because there are no techniques in that chapter itself. So let's go through some of the techniques. Add steel brace frames. These are in concrete buildings. A lot of the issues are the same that Jim just discussed of adding a steel brace frame into a steel building, but some of them are significantly different. You can see examples of this around the city. This is a very large building, and you can see some braces down here. This is a smaller building up here in South of Market that braces have been added as well. So what are the design considerations? Seldom do we have any cases that have actually been tested in a lab. I'll give you one example that has been, but the interaction between the steel and the concrete, you have to be very careful. If you try to add a steel brace frame within a concrete frame and you're trying to use the columns as the columns for the brace frame, the splices may not be adequate for tension, for example. The forces are difficult to transfer from the steel into the concrete and then back into the steel as you go down. So in many cases you may want to add a steel member all the way around here, so get your steel brace frame all in steel, and then just make the connection to the concrete at the diaphragms. You have to worry again about the deformation compatibility between the brace frame and the other concrete frames, the other concrete frame members in the building. You really want to kind of understand again what your client is trying to do. Do the location of these things have to be inside the building? Can they be outside, as Jim showed in that steel building? And then you got to worry about the configuration in terms of where do I put my doors and corridors and so on. The detailing, it's all about connections, connections within the steel brace frame as well as connections from the steel brace frame to the concrete. It's much harder to make these connections than it is to make steel brace frame connections to existing steel, because you can use all the standard connection methodologies, bolts and welds, but for connecting the steel to concrete, it's much more difficult. So you can, some things are pretty straightforward. If you have a very large member, a horizontal member, you can simply do some threaded rods, anchors, and adhesive. I'll explain later there's some deformation compatibility issues about steel collectors in concrete buildings. If you have a very large member that is not going to have very much elastic strain, you don't have much of a problem. If you have just a flat plate you're trying to use as a collector, as I'll explain, you might have some problems with that system. Now you might the temptation is always, if you're going to add a brace frame or a concrete shear wall in a frame building, that you're going to do it right on the grid line, so that the columns will be right smack dab in the middle of your element. That is not always the smartest thing to do. You might want to locate your brace frame or shear wall right off the grid line here, because if it's right here, you have to transfer the shear all the way through this beam. If you put the brace frame or shear wall over on this line, it's much easier to make these transfers. So that's something to consider. In this case, I already showed you the building, but Degenkolb and University of Texas came up with an idea for combining the steel brace frame with a concrete building. There are many buildings in California that have this sort of architectural design where the concrete columns stick out of the building. They are rectangular, so they stick out of the building, and it forms this space outside the building where you might be able to get some steel members. So there were some tests done at Texas of putting in a cross brace system like that, and it worked out very well. When you try to take information directly from a test, you have to be very careful that your conditions in your building are going to actually match the test, because if you change something very slightly, all of a sudden you may not have the same situation. In this case, the test was taken from the field, so it was tested exactly for the building that it was used in, so they didn't have that problem. Now, the interesting thing is when you come up with systems like putting a steel brace frame inside concrete, it's very hard to calculate what the resulting stiffness and strength is. In this particular case, it was very interesting because the sum of the parts was greater than you would ever calculate. So the capacity of this combined system was greater by test than you could possibly calculate. So it turned out to be a very good test efficient system that was developed. In plan, there's a spandrel around the building. This is the spandrel in plan, so this column sticks out like this from the building and forms a space in between columns on the exterior where this diagonal system can be put in. This was the detail that was used to make this connection. There was some pipes that were cored through the column, and this indicates what the procedure was to get all this stuff in. The connection of the whole system to the building. This is a section. So these are the slabs. So this is the diaphragm getting in the load to these horizontal members. So if you add a concrete or masonry shear wall into a concrete building, there's also some issues. This is a building that we added some concrete walls in, and this is the cross section. You can see here these walls were added to basically simulate walls that were already there, so it wasn't going to change the architecture much, and there was locations in all these wings in which to do that. These particular walls were put in this location not only because the shear demanded it, but also it cut down the diaphragm span, so it solved a couple of deficiencies with that location. So this is the cross section. Because of the centrally located corridor, we basically had a coupling beam design that was necessary in order to make this work. We needed a new grade beam because there was nothing there before. Here's the construction. Here is the line of columns that were there, and the excavation for the new grade beam was made around those existing foundations and enveloped by new concrete. Put the reinforcing in and form it up, and you can cast it. This particular project was done in phases. Again, we say over and over and over again, you have to design your retrofit to suit what is the occupation of the building. This particular building was an academic building. The work had to be done during the summer, so you could only do so much work in the first summer, then you had to do the rest of the work the next summer. So all of the foundation work was done in one summer, and at the first level there was going to be a coupling. So these are all couplers. Here is the existing reinforcing in the slab. The other thing, when you cut through a slab, you have to be careful. You're going to lose its vertical support in some cases. This particular one was shored to get this continuous slot, and then the reinforcing was put in with couplers so that the next summer the shear wall could continue its construction. Here was the situation before they covered it up for the use for 9 months of the school year. So the next year they came back and coupled the shear wall steel onto that base and shotcreted the walls and smoothed it out, and it all was fine. The short column is a different deficiency. We've seen this in many earthquakes. The short column simply is a shear critical location in a column because of the fact that there's some kind of a wall, often incidental walls that people don't think about. In this case, this was a full bore concrete wall that was stopped because they wanted windows to let light into this area of the building, and it was creating a really absolute certainty of a failure at that location in this building. And so in this case, this was we negotiated that they didn't really need the windows under the circumstance, so we eliminated the short column by simply filling it up with concrete. In this case, we had shear walls. This rear wall of this building was all basically a frame with windows, and we went in and found certain rooms where they didn't really need the window, so we managed to infill certain areas, and come up with a new shear wall. In the case of the University of Texas, besides doing that system, they also did a lot of research on interconnectivity between new concrete and old concrete. For example, and this is covered in the document, they found out the so-called dry pack, which we've all been using since we were knee-high to a grasshopper. If you put in a new wall up to the slab and then you dry pack that last 1.5 inches or the last 2 inches, that is an absolutely horrible connection. Its capacity is very, very low. So that is not the way to put in a shear wall in a building. So you have to be careful about those kind of considerations that are covered in that chapter. All these connections of old concrete to new concrete, you got to be very, very careful about, and we try to give you as much information as there is available in the research about the right and wrong ways to do it. If you put in a concrete shear wall in a building, you always have to figure out how to get through the slab. If you completely cut a slot there, you have several problems. First of all, you're trying to make a connection from the slab into the wall. There may or may not be enough concrete there. If you cut the slot completely, you have a shoring problem because you've cut the structure. So what we often do is actually make intermittent cuts. So you make a complete cut hole here to get 4 rebars through. Here you just put a single rebar through the existing slab and then alternate this, and you in fact end up eliminating shoring in many cases and still get all of your forces through. Again, as I mentioned, you often might want to put your shear wall location not on a grid line or not on a joist line, because if you put it alongside in a joisted floor, you can come up with a detail like this where you can get a good connection into the diaphragm by drilling into the beams or the joists. So there's a bunch of suggestions here and things to watch out for in putting shear walls in, and again it points out that you might want to make these holes intermittent like this, so to avoid the shoring that would be required if you put a continuous slot in. collectors in concrete diaphragms. This is a diaphragm issue, but we've put some tips into the concrete section because it comes up in every building. There was this research at University of Tennessee on the local connection of new concrete to old concrete. Again, there are certain things that do not work well, but for a collector, you got to worry about strain compatibility. Unless the strain is very low, like a monstrous steel beam next to a concrete slab, you may not have a problem. But if you put a plate on a concrete slab and bolt it in, you're going to have a strain compatibility problem, because the bond slip of a rebar in concrete is not the same as a plate being strained on the top of a concrete slab restrained by bolts, because the bolts have virtually no ductility. So if you start pulling on that plate, the first bolt in line will take all the load and fail, and then the load will be transferred to the next bolt and it will fail. So you get a zipper effect and you simply fail in the entire line. So that is a strain compatibility problem. So you have to be very careful to use a steel plate as a collector. FRP is very, very brittle and very strong. It's very tempting to use it as a collector because it lays flat on the floor, but you have to be very, very careful on how that's detailed. Number one, you got a strain compatibility problem. Number two, you have the problem that it is of this zipper effect that is very hard to rationalize because you can't get the strains compatible. You also have to worry about with shear walls where you're going to how you're going to interface with the existing MEP systems, because almost every building has ducts and pipes going around, and you got the added weight. So we'll look at a couple of examples. If you can use concrete as a collector, you don't really have any problems because you got the strain compatibility problem licked. In this particular configuration, you have to figure out some way to get the concrete in here, so you probably have to have some holes intermittently to be able to cast such a collector as this. If you have a joisted system, again, you have the advantage of having the side walls of the joist, so you can make those connections a little easier. You can add concrete along the side. In all these cases, you have to worry about where you're getting the concrete in. You can see you're talking about pore holes. Every once in a while here, you have to worry about, is this interface between that concrete and this concrete going to be any good? Do you really want to count on that, or you want to count on only the other sides where you have more confidence? So here's a monstrous collector being put in, concrete against concrete. Again, the pore holes were needed from the floor above, and of course, if you're talking about disruption, you're not only worried about this floor, but you're worried about the floor above, because they're actually going to bring the concrete up into this building in the floor above. Steel plate. Well, we needed to have a steel plate collector for a building. I'll show you in a minute. So we devised a way to get around this strain compatibility problem. You basically put in a bolt that has a friction spring washer that with a pre-tension. You put it in a slotted hole. So when you start pulling on the plate, the first bolts will take the load, but it's a known load because it's a friction critical connection. The steel plate will slide along the surface of the concrete and strain as appropriate until the next bolt starts to take its friction load. It will then transfer to the next load. So actually, in a 10-foot length of steel plate, if you need 30 bolts, all 30 bolts will work using this system. If you just bolted everything down, you're going to have 2 bolts work. They're going to fail, and the whole system will fail. So it's something you have to worry about. We use this on this building because this was the old De Young Museum. And our instructions, this was the retrofit to last 5 years, and our instructions from the client was to make it ugly, because they wanted to make it as ugly as possible so they could raise money to say, gee, we need a new building. And in fact, that's where the De Young Museum that Brett Luzundia actually designed was to replace this particular building. But these steel, exterior steel frames went across the top of the roof, and to pour concrete up there was very difficult, so that's where we devised this steel plate connector for collectors to get to these exterior steel braces. Again, it's the same old problem. Exterior solutions are wonderful, but you got to figure out how you're going to get the load to these elements. So here's what one of these collectors look like. This is a piece of steel. All these little vertical guys are these embedded threaded rod embedments with friction with the friction washer in a slotted hole. So when you start pulling on this, all of these bolts are going to end up working. Okay, FRP gets a lot of, has been a huge amount of research on this material. It seems to be a miracle material for retrofit, and it's got a lot of uses, but you have to be a little bit careful. There are several different kinds of different strengths. The glass fiber, they're all very strong, but this is the weakest, so to speak. And carbon and aramid become stronger and stronger. It's basically a thread that's woven to form a bidirectional mesh. You can do it at 45 degrees, at 90 degrees. They're all collected together to form this carbon toe winding, the horsetail I showed you this morning that went around the beam. There's a bunch of these threads you can use to go around corners, or it can be put into prefabricated plates or other shapes. So there's many different forms of using this material. The mesh is the one that is usually used for concrete. It looks like wallpaper or it looks like a fabric, but sometimes you need these toe windings to go through walls if you need this continuity that you can drill a hole and put these horsetails through. Material is very strong but very brittle. The rupture strain is very much less than concrete, creating these compatibility issues that I mentioned. And under the theory that we don't really know how big the earthquake load is going to get, we strongly recommend in this document that you have a fuse somewhere that is going to yield in a predictable way before the FRP yields. If you start looking at the database in other countries for this material, it's very, very large. There's been a lot of testing, but there really is no organization like ACI or something that puts all this together, so you'll get some conflicting design suggestions. We have quite a bit of information in the book. Some of it is controversial. We have been contacted by some FRP manufacturers who weren't particularly happy with some of our warnings, but nevertheless, we as far as we could research, we believe in them all. The connection to the substrate interface can be either contact critical, which simply means that if you wrap this material around a column and the column tries to expand, then it doesn't really need any adhesive. It's simply a hoop stress. So that's the contact critical. The bond critical is much more difficult. That is when you put the material on a shear wall, and the reinforcement of the material for the concrete can only work if it's bonded. And the bonding is basically an adhesive bond, and you can use that for shear enhancement or flexural enhancement. Although and it's used for gravity flexural enhancement a lot. To use it for seismic, you have this issue of unpredictable loads, so it's not particularly recommended in that case for seismic. And if you use it for shear enhancement, as I mentioned this morning, you can make the fuse the flexural strength of the wall, so you can protect the FRP shear reinforcing in that way. You can make it suitable for most environments. However, there are issues. It is susceptible to corrosion and sunlight and fire, temperature changes. But so you have to recognize how you're going to use it. If, for example, you're going to put it on the outside of the building, you actually have to cover it so that it doesn't get UV. And if there is a fire in your building with this material, you're probably going to have to replace it unless you try to protect it, fire-proof it. Constructability, the surface preparation is very important. If you have a very rough surface and you try to put a coating this on, this material basically works in tension, just exactly like shear reinforcing does. And if you start stretching something over an uneven surface, it will tend to straighten out. So whenever there's a depression in the wall, it will try to straighten out and it will pull away from the wall, and you'll end up with a failure in bond. So you have to get the surface relatively smooth. You have to worry about, are you going to cover it up or are you going to leave it there? And while you're putting it in, you may need some controls in the building, both for the other people in the building, the ventilation, as well as humidity for the material itself. So the most common use, and I think it'd be a wonderful use, I mean, we've used it many times, is to put a wrap on columns. You can do that for many reasons. You can do it for shear strengthening of the column. You can add confinement for compression, or you can add confinement to help your longitudinal bar splice, because the more confinement you have in a concrete column, the shorter splice length do you need. So you have to be a little bit careful in all these uses. However, if you were going to wrap a column for shear strengthening, and you put this material all the way down to the base of the foundation or up to the beam or something, this material right here is going to start reinforcing that column in flexure. So all of a sudden you have more flexural capacity than you thought you did, so the flexural capacity of the column is no longer protecting the shear that might go into this material. So if you look very carefully at all Caltrans columns that have FRP wraps, you'll see a little space at the bottom that will prevent this from happening. So the other thing you have to consider, which we cover in the book, is when you're trying to do many of these things together, how many times can you use the FRP? I mean, can you use it to enhance the shear capacity as well as confinement, as well as all the other particular purposes, because it's all producing tension in the FRP. So how can you double dip? There's a lot of discussion about that in the book. So you have to be careful about this interplay, and you have to make sure that the fibers are going in the right direction. If you put the material, for example, on a column and has very many vertical fibers, you're going to enhance the flexural capacity as well. So the recommended sections, if you have a rectangular section, it is recommended you don't exceed a 1.5 to 1 ratio, because the confinement over a long stretch here is not going to work. So if it's round, obviously it works nicely, but the 1.5 to 1 ratio, beyond that you need some kind of a cross tie in order to make the confinement work. Here's an example. When it's all done, it's very neat, and then that's what makes it a popular material. It doesn't increase the column size very much, so it is a good use. On shear walls, I've already showed you the picture of this. This is a residential building, very similar to the hotel motel, although it's a dormitory that has many concrete walls transversely between each room and longitudinal walls at the corridor. It's a double loaded corridor, so it has quite a few walls. It's quite strong, but it's quite brittle because all the walls are shear critical at its base. So we in fact use this material also because we couldn't add concrete because the dimensions of all the rooms and the corridors were so tight that if you added 6 inches of concrete, the thing wouldn't work anymore. So this was about the only material we could use. We did a lot of analysis to convince ourselves that we were only adding shear capacity and that all of these piers could yield in tension from flexure, and this was capacity protected in that way. We also put this on the outside in some places in this building, and we had to put an overlay over the top of this to protect it from UV. There's a lot of little subtle details that you have to worry about. If there's a door in the wall and you have to put this material over the header, these free edges basically don't work. You can't really have a free edge, so you either have to use a horsetail through here to make this a continuous connection, or in bond critical situations you can use these fiber anchors, which are also a product that they have. But again, you have to be concerned about all these edge conditions. At corners, there's another issue in terms of how do you tie this wall into this wall. There's also a shear transfer problem at a corner. If this is I think I have another slide here, but you just need a lot of these fiber anchors at the edges and corners in order to make sure these don't become the weakest points. If you try to take shear around a corner with this material, it's a problem. For example, if you have a wall that you are enhancing with this material and you come to a slab and you want to transfer the load from the wall into the slab, so you just wrap it around the corner. This material is basically working in diagonal tension. So if you think about diagonal tension in the wall and diagonal tension in the horizontal slab, and you pull on both of those things, that material is going to pull away from the wall. So you would have, in order to make such a detail work, you would have to put some sort of a steel angle or tube or something in the corner and bolt it into the wall to take that horizontal force that is trying to pull that material away from that corner as the shear tries to get around the corner. So these are these fiber anchors. They're kind of little mini horsetails that are epoxied into the concrete and then come out and are spread out into the material. And these are sort of semi-structural. I mean, nobody is suggesting that this is all you need to attach the material to the wall, but they enhance the natural adhesive connection, and they certainly will resist a certain amount of tension if this tries to straighten out and tends to pull away from the wall. Questions?